Welcome to the unit on sequences and series, arithmetic series. The objectives for this session are to prove and apply the formula for the sum of an arithmetic series. Before we take a look at arithmetic series, let's review arithmetic sequences. The formula for the nth term of an arithmetic sequence is u subscript n equals a plus n minus 1 times d. Here, u subscript n is the nth term, a is the first term of the sequence, and d is the common difference. So let's take a look at an example. The sequence 3, 7, 11, 15, and so on is an example of an arithmetic sequence because we're adding by the same amount each time. So plus 4 here, plus 4 here, and plus 4 here. An arithmetic series is the sum of the terms of an arithmetic sequence. So, for example, an arithmetic series can take the form 3 plus 7 plus 11 plus 15. We've added the terms of the arithmetic sequence. S subscript n denotes the sum of the first n terms of a series. So in this example, S subscript 4 is equal to 3 plus 7 plus 11 plus 15, which is equal to 36. Let's now take a look at another example. We're going to prove that the sum of the first 75 natural numbers is 2,850. The sum of the first 75 natural numbers can be written as S subscript 75 equals 1 plus 2 plus 3 plus and so on all the way up to plus 73 plus 74 and plus 75. We can write this in the reverse order as 75 plus 74 plus 73 plus all the way down to 3 plus 2 plus 1. And there is a reason for doing that, because when we add the two sequences, one in the right order and one in the reverse order, we obtain 2 times S subscript n, or S subscript 75, equals 1 plus 75, which is 76, plus 2 plus 74, which is 76, plus 3 plus 73, which is 76, and so on, all the way down to 73 plus 3, which is 76, plus 74 plus 2, which is 76, and 75 plus 1, which is also 76. So therefore, we have that 2 times S subscript 75 equals 75, because there are 75 of these 76s, so 75 times 76, which is equal to 5,700. And therefore we have that S subscript 75 is equal to 2,850. Now let's take a look at another example. We're going to prove a more general form of this sum. Prove that the sum of an arithmetic series is S subscript n equals n over 2 times 2a plus n minus 1 times d. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. Again, as before, in the more specific form, we're going to write out the terms of the sum and the terms reversed as well. So Sn equals a plus d plus all the way up to plus a plus n minus 2 times d plus a plus n minus 1 times d. And then in the reverse order. So we begin with a plus n minus 1 times d and end with the term a. If we add these, we have 2 times s subscript n equals 2a plus n minus 1 times d, because we're adding a and a plus n minus 1 times d, plus, again, 2a plus n minus 1 times d, because this time we're adding a plus d plus a plus n minus 2 times d. And all the way down to 2a plus n minus 1 times d again, add, for the final term, 2a plus n minus 1 times d. So therefore we have that 2 times Sn equals, and because there are n terms in this series, or n separate parts of this equation that we're adding together, multiplied by 2a plus n minus 1 times d. And so dividing through by 2, we have that s subscript n is, as required, n over 2 times 2a plus n minus 1 times d. This formula can also be written as Sn equals n over 2 times a plus l, where a is the first term and l is the last term. And this, of course, is the case for any arithmetic series. Let's now take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A first. We are required to find the sum of the first 100 terms of the arithmetic series 14 plus 17 plus 20 plus 23 plus 26 and so on. So let's solve this. We're going to begin by writing down the values of a and d. A is the first term, so therefore a is equal to 14. And d is the common difference. So we can calculate that from the first two terms, which are 14 and 17. Therefore d is equal to 17 minus 14. And this gives us that d equals 3. We can now substitute the values for n, a and d into the formula for s subscript n. So we have that s subscript n, or s subscript 100 if we want to be more accurate, is equal to n, which is 100, divided by 2, multiplied by, and in brackets, 2 times a, which is 14, plus n minus 1, which is 100 minus 1, times d, which is equal to 3. And therefore we have that s subscript n equals 16,250. We've simply tidied up this formula, or carried out the calculation. And now for part B. In the same arithmetic series, we are required to find the least number of terms required for the sum to exceed 1000. So let's solve this. In our question, we're given that this series is greater than 1000. This is what we actually need. And we want the smallest n, which is going to satisfy that. Now from part A, we know that A equals 14 and D equals 3. We're also going to let S subscript n equal 1000. Remember, we want the smallest n, which allows the sum to exceed 1000, or S subscript n to exceed 1000. We now substitute these values into the formula for S subscript n to give Sn equals 1000 equals the number of terms n, which is what we're looking for, divided by 2 multiplied by 2 times A equals 14 plus n, again, because that's what we're looking for, and that's part of the formula, minus 1 multiplied by D, which is equal to 3. If we tidy up and rearrange and multiply through by 2, we obtain this quadratic, 3n squared plus 25n minus 2000 equals 0. And solving this quadratic gives us two roots, n equals 21.99 or n equals minus 30.22. Now, since n is the number of terms, we can't have a negative value for n. And therefore, we can conclude that 22 terms are needed in order for the sum to exceed 1000. This brings us to the end of this session. If you have understood its contents, you should be able to prove and apply the formula for the sum of an arithmetic series. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.